The
Okay.
broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Thank you so much for the wait here. We had multiple difficulties, I think, between myself as the organizer, Yuna, and David. We each had our own respective difficulties this time. So anyway, yes, we were a bit late, but thanks for bearing with. I'm going to have to end up driving the slides and so forth today. And I think you can all see my screen. And um, and so I'm not going to be able to really run the notes document here. So we will take a quick break at the end, and hopefully you guys will be able to unmute. Or you guys can raise your hand and I call on you for questions if we have time at the end of each presentation. And rather than introduce everything, because I know we're running late, we will start right in with our first talk of the day, which will be followed by David Marsico talk after Yuna Lim's talk on land atmosphere coupling and surface air temperature prediction. So I'm going to turn it over to Yuna.
Thank you, Mark. Hello, my name is Yuna Lim. I'm working at NASA GMAO and ESIC at University of Maryland College Park as an assistant research scientist. Thank you for inviting me to present my work in this week 3 to 4 webinar. Today I'll talk about the role of land atmosphere coupling in subseasonal surface air temperature prediction. This work is done with Andrea Molod, Randy Koster, and Joe Santanello. Actually, in the abstract, I planned to show some results about the string flow prediction in our offline catchment model, but time was limited, so I decided to only show this topic in this webinar. But if I have any chance in the next time, I will do that. Yes, next slide. So some of you are already familiar with this figure. This figure shows how predictable each forecast range is. So x-axis is the forecast range and y-axis is the forecast skill. So in the weather forecast, the predictability is relatively high, and it comes from the initial atmospheric condition. On the other hand, the seasonal outlook, it is also the predictability is somewhat stable, and it comes mostly from the sea surface temperature condition. But however, compared to weather forecasts and seasonal outlook, week 3 to 4 forecasts, the predictability is relatively very low. So in order to better utilize our forecast output, people try to find when or where the predictability might increase or decrease using the initial condition of related phenomena having long memory in subseasonal timescale. Please. So it is also referred to as the windows of opportunity for skillful forecast. Please. So one of the key sources of subseasonal prediction is land component. This figure is from Koster and Soret 2013. In terms of the seasonal forecast, they did Amy-Todd experiment with soil moisture initialization and without soil moisture initialization. This figure, the left figure shows the soil moisture difference between two experiments, and right figure shows the difference of 2-meter temperature forecast between two experiments. As you see, over the northern Great Plains and eastern Great Plain area show big difference. Depends on the soil moisture initialization. Switch. And in terms of the subseasonal forecast too, the Meyer et al. 2018 also show that the importance of the initial soil moisture information. This figure shows the 2-meter temperature prediction scale. 2-meter temperature prediction scale. So red line means that the forecast prediction scale from the forecast without land initialization, and green line is the same but with land initial condition experiment. This bottom line, you can see the orange shaded area. That this means their difference between two experiments. As you see, the difference starts at maximized at 10 to 15 days, and their difference maintains up to a month. So based on this, results, previous studies have improved the importance of improved understanding the impact of the soil moisture initialization, or found some forecasts of opportunity using the initial soil moisture conditions. However, for soil moisture to have an impact, it must be accompanied by land-atmosphere coupling processes. Switch. So this is the one of the this schematic diagram shows one of the key land-atmosphere coupling processes, which is also the focus of our study. Focus of our study. So, which I will briefly explain. Oh, I see. Oh, okay. Oh, yeah, stop here. Okay, then I will briefly explain the schematic diagram first. So if the soil moisture is dry, then the latent heat flux is decreased. As a result of the reduced evaporative cooling, the surface and lower atmosphere warm up and relative humidity decreases. This leads to a reduction of the lifting condensation level deficit, and which creates less favorable condition of developing the precipitation. So this kinds of positive feedback helps to maintain the impact of the soil moisture for longer time. In our study, we hypothesized that this coupling process is important. So we built two scientific questions, looks like in the right sentences. So first one is, does a strong land atmosphere coupling increase 2-meter temperature scale? And second one, as you see the schematic diagram, there are many variables are connected in the land atmosphere coupling. We are interested in whether all connections between all variables are meaningful for finding a forecast opportunity or not. So our second question is investigate whether the prediction skill increase with deeper coupling across multiple metrics. Sweet. I will explain the data and method. I used reforecast data set in NASA's GEOS S2S version 2 model, which is initialized from 1999 to 2022. In this study, we focused on the Boreal summer impact. So the reforecast initialized June, July, August are used in here. So total number of reforecasts is 414, and ensemble size was 4. We are targeting the 2-meter temperature prediction scale, so we evaluate their prediction scale using the anomaly correlation coefficient as shown below, and we compared it to ERA5 data, it is because we also have the MERA2 data set, but we acknowledge that in the ERA5 data system, their data assimilation system, it ingests more amount of data set from the 2 meter temperature information from ground station. So we decide it is more trustworthy data set as a reference in this analysis. So we compared it to ERA5 data set. Right. And then I will explain which land atmosphere coupling matrix is used in here. As I mentioned earlier, our second scientific question was that whether all connections between all variables are important or not in this work. So we consider, based on the correlation matrix, we defined 3 different correlation metrics. First one is the soil moisture and latent heat flux relationship. And second one is the correlation between latent heat flux and skin temperature. And bottom one, the last one is the correlation between latent heat flux and LCL deficit. As you see the mathematical formation, then you can see the ensemble number size and forecast lead time is written. So as you see this information, we used the forecast data set for detecting the land atmosphere coupling processes. It is because our hypothesis is based on the model should have the land atmosphere coupling strongly or not strongly. So that is why we are using we made these indices based on the forecast data set. So, and then using these 3 indices, we defined strong coupling index. For example, if all 3 indices are indicating strong land atmosphere coupling based on the 50 percentile value, we decided the reforecast has strong land atmosphere coupling. On the other hand, all 3 indices are indicating weak coupling event, then we decided as the weak coupling events. Please. Before examining the impact of land atmosphere coupling processes on the surface air temperature prediction scale, we evaluate the general performance of land atmosphere coupling simulation in our S2S version 2 model. The left column shows the mean value of 3 different land atmosphere coupling index averaged over all reforecast data set. And the top figure shows the relationship between soil moisture and latent heat flux, and middle one is based on the second matrix. And third one is based on the bottom one is based on the third metric, correlation between latent heat flux and lifting condensation level deficit. And then for comparison, we made same data set using the ERA5 data set and MERA2 data set, which are shown in the second columns and rightmost columns. As you see, the maximum value is shown in the Western United States, and relatively weaker value is shown in the Eastern United States. These kinds of overall spatial distributions are similar between reforecast and the analysis data set. And also the S2S version 2 model, the values falls between ERA5 and MERA2 data set. Based on this result, we conclude that this S2S version 2 model is suitable for examining the impact of the land atmosphere coupling. Wait, please. So this is one of the key results of our study. As I mentioned earlier, we are interested in week 3 to forecast in the 2-meter temperature prediction scale to show that in the left figure, we showed the anomaly correlation coefficient of 2-meter temperature at week 3 to 4 weeks forecast lead time. And middle one is the same analysis, but based on the reforecast having strong land atmosphere coupling processes. As I mentioned in the data method, these strong groups are defined when all three indices are indicating strong land atmosphere coupling using the 50 percentile value. Right one is the anomaly correlation coefficient, but based on the weak coupling groups. As you see, there is a big difference over the Midwest area and Northern Great Plains between two groups to show that their difference more clearly. I also show their difference in the bottom figure. And also, we shaded only the statistically significant difference regions. As you see, there is a big difference between two groups with a positive difference. So we conclude that we could know that the prediction skill increases with the land atmosphere coupling strength over the Northern Great Plains and Midwest area. Switch, please. So we could, based on this result, we could answer the first question. Switch, please. As you see, and could you? Yeah, okay. Thank you. Okay. In the previous slide, we found big difference over the Midwest area, Midwest region. Focusing on that area, we try to answer the second scientific question. Switch. Yeah, our second scientific question is that whether the prediction skill increased with deeper coupling across multiple metrics. To answer this question, we added two additional groups in our analysis. As you see, there are red bar and blue bar in here. So these 3 strong and 3 weak group are the same with the strong and weak group in the previous slide, based on their definitions are based on the 3 indices are all strong or all weak. And we added 2 additional groups in here. So orange one is called for 2 strong and 1 weak group. So if the 2 indices, it is defined when the reforecast have, if the 2 indices are detecting strong land atmosphere coupling and the other one is detecting weak coupling, then we defined it as this orange group. And also we additionally defined yellow one group. Yellow one group is based on the reforecast where the only one index is detecting strong land atmosphere coupling and the other 2 are having weak coupling processes. So if you focus on left 5 bars, so this is the ACC in each group, and at week 3 to 4 forecast, if you so changing this color bar, changing this color bar, the land atmosphere coupling is more deeply connected from deeply connected. So if you compare this all bars, then you can find 2-meter temperature prediction skill increases with how many land atmosphere coupling is connected deeply or not. So you can see the gradual difference in here. Not only the 3 to 4 weeks forecast, we found that similar result in the week 1 to 4 forecast. In the right 5 bars showing that result. However, as we already know, 1 to 2 weeks of forecasts are affected not only from the land component, but also the initial atmosphere component. So their difference is slightly slightly smaller compared to week 3 to 4 forecast, but this approach is still meaningful in the week 1 to 4 forecasts. So we could answer this question. Switch, please. Yeah. We could answer that when the land atmosphere coupling is deeply connected from the soil to the free troposphere, the prediction skill significantly increases. And also in the bottom line of the figure, we also show the sample size of each group. As we are using the 50 percentile value to separate each group, we expected this red bar and blue bar should have the 1/8 of total sample size. However, their sample size are larger than we expected. It means that at least in our forecast system, we could know that all 3 indices are not independent to each other. Switch, please. Yeah. To further understanding the characteristics of the strong land atmosphere coupling processes, we examine the composite of 2-meter temperature forecast and 2-meter temperature anomaly forecast and 2-meter specific humidity anomaly. And in the right side figure, we showed soil moisture composite with forecast lead time. As you focus on this red line, it is based on the composite of 3 strong groups. As you see, the 3 strong group has a warm and dry condition with relatively dry soil moisture. These kinds of characteristics is shown up at the first initial forecast lead time and maintains for 4 weeks. And then, based on this idea, we apply to answer. We further examine our approach. We further examine the possible impact on the extreme events. Switch, please. Yes. So, for example, the abnormally warm event. Based on the 1 standard deviation value, we defined the abnormally warm events in the ERA5, and also independently, we defined this event in the S2S version 2 model. So we examine how predictable these abnormally warm events are in the S2S version 2 model. If you see this in left column is from the week. All 3 indices are detecting strong cases, and right one is 3-week groups. So as you see this left figure, in the Midwest area, above 50 percentile value, 50% of abnormally warm events is predicted. It means that this approach can be applicable for finding forecast opportunity of abnormally warm events. We can, yeah. Next slide. So this is summary. Yeah, first the finding when the strong land atmosphere coupling is detected at week 3 to 4 forecast, the prediction scale for 2-meter temperature is enhanced across the Midwest area at this forecast lead time. And if the land atmosphere coupling is deeply connected from the soil to the atmosphere, we could find that the prediction scale increases. And then also this kinds of strong land atmosphere coupling was related with warm and dry anomalies. We could also find that improved prediction of abnormally warm events based on the land atmosphere coupling processes. Switch, please. Yeah, and it based until now, yeah, it is obvious. Some of you are interested in this work can be applicable other season or other region like that. Yes, so we are also doing that work, focusing on the boreal springtime over the Konas area. This is the same. This is the same plot, but based on the hindcast initialized boreal springtime. You can see in the right figure they show some difference, but slightly more northeastern United States area. We found that not shown in here. We found that their characteristics are somewhat different with the boreal summer, so we are still working on it. Switch, please. Yeah, this is all I have today. If you have any questions, please feel free to ask me. Thank you.
Okay, thank you. We are unfortunately going to have to move on due to our late start here. Do you care to give out an email address to take any
Yes,
questions?
of course. Yes, I will.
In fact, if you can actually just put it in the chat to the entire audience there.
Okay.
And then we can move on here to David. So thank you very much, Una.
Thank you.
And let us see. Okay. So, David, are you there?
Yes.
Great. I will just let you take it away and get going on your talk.
Great. Thanks, Mark. So I'll be talking about dynamical filtering of tropical subseasonal variability in observations and forecast models. So this is I think, sorry, I can't see the screen anymore.
Okay, can you still not see it?
Yeah, the screen just vanished on my end.
Hang on here. Yeah, that is weird. Let's try something here.
Oh,
Yeah, okay, I'm
Okay.
going to just try switching it back to me here again. And can you see it at all? That must be a no.
Yeah, sorry, I can't can't see it.
Okay. We were never able to get you to be able to present, were we? Why is this?
Oh, I can see it now.
Okay.
I'm not sure what happened.
Let me try something again, hopefully.
Oh, now it went. Oh, now it's back. Sorry.
Is it back?
Is it? Yeah, so I can see the background slide. Oh,
There.
yep, changed back to, okay, great.
Okay, good.
Sorry about
Okay,
that.
I have no
I don't
idea
know.
what's going on today. There are
Yeah.
gremlins here.
Okay. Yeah, so I'll try to keep this quick. Yeah, so this is what I'm talking about. I think I mentioned the title. This is a joint work with my colleagues at Ceres, NOAA PSL, and also the Climate Prediction Center. Okay, next. So just brief background. So much of the forecast skill at weeks 3-4 over North America comes from teleconnections due to tropical modes of variability, such as MJO and ENSO. So the question we tried to answer is, how do we identify or filter these modes from data? So the main idea of our approach is to use what we call a dynamical filter. So this would be, instead of empirical orthogonal function, EOF, or spectral approaches, to identify or to filter modes of tropical variability. Next. Right, so just brief outline. So this so-called dynamical filter is based on what's called a linear inverse model. I'll abbreviate that as LIM, L-I-M. So I'll devote some background on the description of those models. And then specifically how we construct a linear inverse model of a simplified coupled atmosphere ocean model of the tropics, a description of the dynamical filter, and then three applications of our dynamical filter, right? We can use it to show that existing MJO indices convolve or intertwine several distinct dynamical processes. We can then use that to define a new dynamics-based MJO index that can cleanly separate the impact or filter out the impact of ENSO. And then finally, we can use it to highlight the important role of constructive interference between different dynamical processes in driving predictable signals at long lead times. Okay, next. Right, so just a background on linear inverse models. So we model our system as a system of stochastic differential equations. dx dt equals Lx plus Kasai. So Lx, this represents the slow timescale processes. So L here is a matrix that captures the linear dynamics that are potentially predictable on subseasonal timescales. And Kasai, this is just a random forcing terms that represents relatively fast timescale processes. So these are rapidly decorrelating processes that are unlikely to be predictable on subseasonal timescales. And we model it as white noise forcing in time, but it has some spatial covariance structure. Next. Okay, so we can actually write down an exact equation for the matrix L. That's really the sort of crucial aspect of our dynamical filter. The specific form is not super important, but I thought I would at least highlight the role of two matrices. It involves the covariance matrix of a state vector X multiplied by a lagged covariance matrix of X. So I just want to sort of emphasize the difference between our approach and that of standard EOF methods. In contrast to EOFs, which would just basically be the covariance matrix, our L matrix here has this lagged covariance component as well. Next. Yeah, so I'll just briefly mention that, so in practice, L would be some n by n matrix. X is just an n component state vector, and then psi is just some n component noise vector. So the important aspect of L are its eigenvectors and eigenvalues, and they yield the space-time structure of the deterministic and therefore potentially predictable processes, right? So the eigenvectors correspond to spatial patterns. The real component of the eigenvalue corresponds to an e-folding time, right? So that's the amount of time it takes for an initial disturbance to have its amplitude decay by a factor of e. So that's like around 3. And then the complex part of the eigenvalue denotes the frequency or period of oscillation of each mode. Next. So just brief description on how we constructed a linear inverse model, right? So we train it on about 40 years of winter era 5 data. So that's November 1st to May 1st. Our variables are upper and lower tropospheric, meridional, and zonal winds, sea surface temperatures, and outgoing long wave radiation. So that's OLR. So this is in a band around the equator from 24 south to 24 north. Next slide. Yeah, so this is basically just a description of the temporal that's on the left and the spatial structure of the eigenmodes of that matrix L that I showed on the previous slide. So an eigenmode is just an eigenvalue eigenvector pair. So the idea, we show it on the left, we can sort our eigenvalues in terms of their e-folding time. That's essentially how fast they decay, and frequency on the left here. So I'll just basically briefly summarize this. We get 4 different sets of eigenmodes. The black dots show the fast decaying processes. So these are processes that decay very rapidly. There's a slow propagating MJO mode. There's a fast propagating MJO mode. And there's a set of modes indicated by green here that represent ENSO diversity, right? So we have 4 distinct sets or subspaces of modes of that linear deterministic matrix in our limb. Next slide. So the idea behind this dynamical filter is that we can decompose or write any field as the sum of its contributions from the fast decaying processes. Again, these are the relatively unpredictable ones. The contributions from the slow propagating MJO component, the fast propagating MJO component, and ENSO, right? So when I say apply the dynamical filter to a field, what that means is just determine the portion of some field that is accounted for by each one of these sets of eigenmodes of L. Next slide. Okay, so this slide is the first application of our dynamical filter, and we can use it to filter RMM-based MJO composites. So that's shown in the right column here. So the shading is OLR, and the vector fields are 850 millibar winds. So, you can see that RMM clearly identifies the convection that starts in the Indian Ocean and propagates eastward until it eventually dies out over the Central Pacific. And using the dynamical filter, we can actually show that RMM is essentially made up of 3 dynamical processes. There's the fast MJO component, right? So this actually captures the propagating features of the MJO. There's a slow MJO component with a strong amplitude during phases 6 and 7, and a small but non-negligible ENSO component. So I should, an important part to highlight here is that RMM doesn't entirely remove the impact of ENSO on the MJO, right? It's small, but not negligible. So if we did want to define a new an MJO index that can more effectively remove the impact of ENSO, we can do that using our dynamical filter. I'll skip the mathematical details and just show what we get. So next slide. Right, so we can define an MJO index that can capture the propagating features of the MJO, right? That's the left-hand column, while completely removing the impact of ENSO, right? If you notice the third column, there's no ENSO present here, right? So using this dynamical filter, we can define an MJO index that can more effectively or cleanly separate the impact of the MJO on the propagating features of, remove the impact of ENSO on the MJO. Okay, next slide. Sorry, I'm going a bit fast here, but we're almost out of time. So this is those are the first two applications of our dynamical filter. I'll highlight the third here, and that's that the filter can sort of emphasize the role of constructive interference between these three dynamical processes that could drive or potentially drive predictable signals at long lead times. Right? So this is just a composite Hofmahler of the RMM-based MJO shown on the right here. Again, the shading is OLR. The winds, the vector field is the lower tropospheric winds. So using the dynamical filter, we can show that the relatively strong convection over the maritime continent at relatively long lead times, so that's at about 25 days, is actually due to the constructive interference between these three dynamical processes, right? We have ENSO, the slow propagating component of the MJO, and the fast propagating component of the MJO. So that although individually these three processes have relatively weak convection over the maritime continent at long lead times, they combine constructively to give a very strong signal over the maritime continent at longer lead times. Next slide. So this is basically just the same thing. So the results on the previous three slides were based on ERA 5 reanalysis data, and we can do the same thing. We've started to do the same thing using IFS reforecasts. So the top row of this figure is just what I showed on the previous slide. In the bottom are the results we get when we apply the dynamical filter to a composite Hofmahler of the RMM-based MJO. So that's H here, right? So you can clearly see that the propagating features of the MJO are captured, albeit relatively weaker and somewhat faster than what we see for ERA 5 data. But you can still see sort of the same pattern, right? The strong convection, the strong negative convection over the maritime continent, it's a bit hard to see, at relatively long lead times is due to the constructive interference between the three dynamical processes of ENSO, the slow propagating MJO, and the fast propagating MJO. Even though these individually, these processes don't perfectly resemble what they look like in ERA 5 data, they still interfere constructively in exactly the same manner to produce this stronger convection at long lead times. Next slide. Okay, yeah, so that's my talk. I know I went through that a bit quickly, so I'll just sort of summarize the main points here. So we designed a dynamical filter of tropical variability based on the eigenmodes of a linear inverse model, and that reveals that RMM, say, convolves or intertwines several different dynamical processes, including ENSO. And then we used our dynamical filter to define a new MJO index that could cleanly separate the propagating features of the MJO from ENSO. And then finally, we used this dynamical filter to identify processes that interfere constructively at long lead times, which is critical for driving potentially predictable signals at those long lead times. All right, so that's it. Thanks, Mark.
All right. Well, thank you, David. I'm impressed in how much you actually got through in that amount of time. That was pretty impressive, but that was very interesting. And I'd like to, we have a couple of minutes here due to your efficiency, if anybody has any questions for you.
Sure.
Let's see. I want to see if there's anything questions pane. Did that open up properly? Okay. Says David, is the IFS-based MJO fast mode much faster than in the ERA 5 observational analysis?
Yeah, so if you could go back to the previous slide. So short answer, it's actually a bit slower. Yeah, so the total field is faster, but when you apply the filter, it turns out that the fast propagating MJO is actually slightly slower than it is in ERA 5. Yeah.
Awesome, thank you. Now let me see. Okay, yeah, Matt had a comment there previously, not being able to see you. Yeah, that was. So anything else? Any other questions? You can type it in the questions pane, the chat pane. Okay, well, I will speak for just a minute here while if anybody has any other questions, but I basically just want to apologize for the technical difficulties. Some of that is, I believe, my PC at work here, but so I could be making a visit to IT. But I appreciate everybody for standing by and waiting for the talks and for speakers for bear with everybody, bear with me as well here. Anyway, I don't see any other questions come in, so we will go ahead and wrap up. And I want to thank both David and Una again for their talks. Very interesting. And we will be reaching back out again about the next seminar. So thank you very much.
Thank you.
Thanks. Thank you.